Yes, can you see the screen also? Shashank?
Yes, sir.
Okay. So we just start with the session. In a previous session, we talked about the different. Actually, we are learning the dimensional analysis and similitudes. Okay, this is our chapter. In a previous chapter, in a previous session, we just talked about the different aspects on model and prototype. Okay, so we are at the stage of finishing the chapter. So we talked about model and prototype. So in that we have seen that uh, model is an actually yes, actually it's a replica of the actual structure that we say it as model, and prototype is an actual structure. So again, in that we have seen the different advantage of model testing and applications where it can be applied, like the flood control and irrigation channel, turbine pumps and compressors. Then we talked about similitudes. Similitudes is basically similarity between model and prototype in every respect. Okay, like first is say the geometrical similarity, then kinematic similarity and dynamic similarity. This we have covered up in last session. So in case of a geometric similarity, also we talked about the dimensions. If the model and prototype are similar in terms of dimension, we just model to the width of model. Okay, that type of the solution, we say it as the geometrical similarities. And we have seen that how to write the scale ratios of uh, in different aspects, like a scale ratio or the area scale ratio or the volume scale ratio. So if I have to write area scale ratio, I just have to write in terms of area, like area. If I just write it, you can see in the paint, that is, suppose I have to write area scale ratio, so I can write it as a length into width. Okay, so this is the length of suppose model and this is width of model. Okay, divided by length of prototype into width of prototype. So in this way, I just have to write the area scale ratio. Area scale ratio, because we have a formula, no? Area is equal to length into width. But to write the area scale ratio, this is the format. We just write it at the okay, LM by LP. I just say this as LR. Okay. The scale ratio. Okay. Now how to write scale ratio? Scale ratio is nothing but I just told you uh, that if I just have to write length of model to the length of prototype, okay, then I just say it as the scale ratio LR. This is the way to write scale ratio. Okay, the similar way I just have can write width of model to the width of prototype. Okay, that also I just have, can write LR. This is LR. You just say this is scale ratio. Now you can see here this area scale ratio. I just write it as LR, okay, multiplied by the another width of model to the width of prototype. I just make a correction here, width of prototype. So this can also, I just write it as LR. So LR into LR is LR square. So this is the way to write area scale ratio, and this is only the scale ratio. Okay. Next is volume scale ratio. Volume scale ratio. Okay. So how to write volume scale ratio? We know the formula for volume, that is L cube. Okay. L cube, instead of writing directly the L cube, I just write it as uh, LB into H. Okay. So LB multiplied by H. So I just say this is the length of model. In a previous lecture, we have seen that model is something lesser dimension like this. Okay, if I draw a diagram here, just see here. Okay, on a smaller scale, I just prepare a model. Okay, length. This is length. This is width, and this is height h. Okay, and prototype. This is a model. Okay, on a smaller scale, and prototype, that is same model, but I just make it on a larger scale like this. Okay, so this is our prototype. Now prototype is an actual structure. Now how can you say that prototype? So if you imagine a dam structure, okay, if I just make a model of the dam in a smaller scale, and prototype is an actual dam. Okay, so you can just analyze the example by this thing. Okay, so same notation if I give here, that is h, then height h, then width b. Just make it a small, and so small b. Yes, and this is length L. Now I just make it clear that which is model and which is prototype. So I just write it as prefix, that is LM. This is BM and this is HM. Okay. The same way for the prototype, I just write it as SP. This is BP and this is LP. Okay. The same thing I have written here. You can just see on the left side. The same question I have written. Okay, so divided by okay, this is for if I'm writing for volume, then LB into H, then width into height. Okay, volume scale ratio of model and prototype. So I just write model for M, okay, and height divided by for prototype. So length for prototype multiplied by width for prototype into HP. Okay, so if you again see that LM by LP, that is actually LR scale ratio divided multiplied by the next term. If you see BM by BP, that is again LR. Okay, multiplied by HM by HP, that is again LR. So if you multiply all these terms, you get LR. So this is a volume scale ratio in case of geometrical similarity. Okay. Next is Kinematic similarity. So in case of kinematic similarity, we just write down the kinematic scale ratios in terms of velocity and acceleration. The same thing, but only you just change the data by velocity and acceleration. After that, dynamic similarity we have seen. Dynamic similarity is nothing but the in terms of forces. Okay, so you just remember that geometrical is for the dimension purpose, then uh, kinematic similarity is for the velocity and acceleration purpose. Okay, and dynamic similarity is for force. If I have to write the forces term, so that only I'm going dynamic. We just revise. Then we'll move to the next topic. That is a model law or a similarity law. Okay, so model laws are model law or similarity law. Okay, so the ratio of the corresponding forces at the corresponding points in model and prototype should be equal for the dynamic similarity of model and prototype. So that means the dimensional number should be same for the model as well as the prototype. So if we just talk about the different laws like Reynolds model law, then Ford model law, Euler's model law, Weber model laws, then Mach model laws. So basically these are the dimensionless numbers like Reynolds number, Ford number. We have seen in previous lectures also. Ford number, then Euler, Weber, and Mach numbers. These are dimensionless numbers. Okay, so I just solve only one that is law. Okay, rest of the laws are you just see that that's an easier one. You can remember it also. Okay, so I just start with the Reynolds model law. First is Reynolds model law. Okay, so this law in which models are based on Reynolds number. This we call it as Reynolds model. And viscous forces are predominant over the inertia or other forces for the dynamic similarity. So the Reynolds number for the model must be equal to the Reynolds number for the prototype. So you just see that this is Reynolds number for prototype. That is equal to Reynolds number for model. What is the formula for Reynolds number? That is R is equal to rho V D by mu. Okay. So you just write rho V into D. Instead of D, you can also write it as L divided by, because if you see the dimensional terms, D you can calculate in meters and L is also you just calculate in meters. Rho V D by mu. So if I am writing for prototype, we just write it as suffix P. Okay. P. That is equal to same, and on the right hand side rho V L divided by mu. But this is for model. Okay. Now, if I have to write in scale ratio, how to write it? So just divide the right side to the left side. So rho p can I directly rearrange it? So rho p divided by rho m, okay, multiplied by Vp divided by Vm, Okay, multiplied by LP divided by LM, multiplied by 1 divided by mu P divided by mu is equal to 1. Okay, only I have taken right side to the denominator. So rho P divided by rho M, can I write as a scale ratio LR? Sorry, instead of LR, rho P divided by rho M, now I just change the notation, that is, I just say it as rho R. In the similar way, Vp divided by Vm, that is Vr, velocity scale ratio, and LR is the scale ratio. Okay, divided by mu R is equal to 1. Now, you just see that these are nothing but the scale ratio. What are scale ratio? I just write it here. Scale ratio. Okay, that is rho R. Now, what is rho R? You just see that is rho P divided by rho R. In the previous term, we are writing it. Then velocity ratio, we have taken Vp divided by Vm. Okay. In the same way, LR, LP divided by LM. LP divided by LM. Then mu R, that is mu P divided by mu R. These are the scale ratio. Okay. Then in the same way, can we write the time scale ratio? So how to write time scale ratio? Okay, so time scale ratio is equal to, if you see the formula, that is speed equal to distance upon time. So time is equal to distance upon speed. Okay, so distance we just write it as a length. Okay, and speed is nothing but in terms of velocity. So we are like this. Okay, so this is the time scale ratio. In the same way, you can write velocity scale ratio. Okay, or acceleration scale ratio. If I have to write acceleration scale ratio, okay, so acceleration AR is equal to, acceleration is equal to speed divided by or velocity divided by time. So velocity scale ratio divided by time scale ratio, like this. Okay. In the same way for the force scale ratio. So you just modify all the terms in case of scale ratio. So this is what about the Reynolds model law. In the same way, you just have to write for the broad models law. So basically, a few things are important in case of the broad models law. Broad model law. So actually, the broad model law is used in the we just say when the gravity forces are predominant over the other forces for the dynamic similarity. Okay, that time we just use the broad models law, and Reynolds we just use in a closed pipe. Okay, or the airplane or submarines. So we just have a formula for the broad models law we have derived, that is V divided by under root G into L. Okay, this is the formula for the broad models law, and the same way just write the scale ratio for the fraud models. Now, only one thing you should remember when you are writing for the discharge scale ratio. Always this term is asked everywhere. That is discharge scale ratio. Okay. So if you see any term like force scale ratio, discharge scale ratio, density ratio, okay, density scale ratio, viscosity scale ratio, or any uh, dependent terms, we just say that uh, like viscosity, okay, or anything. So if you are writing in a scale ratio, you have to simplify it in terms of scale ratios only. So this is QR is equal to LR raised to 5 by 2. So just see that how it comes. If you see in the textbook, you can understand it easily. That is not much difficult. Okay, so we just see the some problems based on this. Before that, we just talked about few uh, terms like distorted models. So distorted models are those which are not perfectly geometrically similar to the prototype. Okay, so this type we just say it as the distorted model. Particularly in case of shallow rivers where depth is small compared to width, and without distortion, the depth of flow in a model will be so small that measurement may not be accurate, and surface tension effect will be predominant, which will not be present in a prototype. So hence it is necessary to distort the model in a vertical direction. Okay, so next is we just say the advantage for this distorted model is used. It is used in hydraulic similitudes or turbulent flow in a model that is become possible by this, and cost of models can be reduced. Then if we see in terms of disadvantage due to different scales in different direction, velocity and pressure distribution in a model is not the same as that of prototype. So some advantage and some disadvantages are there for the distorted models. Then next is undistorted model. Okay, undistorted model. So distorted model is not perfectly geometrically similar to the prototype. Okay, and undistorted is those which are perfectly similar to all respect. Perfectly similar in all respect. Okay, so this is what about the distorted and undistorted models. Next, we just start with the some problem numericals. So if you see a pipe diameter of 1.5 meter is required to transport an oil of specific gravity 0.9 and viscosity 3 into 10 to the power minus 2 poise at the rate of 3000 liter per second. Okay, so the diameter of the prototype. Okay, diameter of prototype. This is means the actual diameter of pipe, that is 1.5 meter. Just write it as prototype. Prototype. We just clear it first. Prototype. Okay, so for the prototype, the diameter of pipe, that is 1.5 meter. Then what it says, it is required to transport an oil of a specific gravity, that is specific gravity for the prototype. Okay, I have only this model. This is prototype P. That is equal to 0.9 specific gravity of oil. Okay, oil. Then viscosity mu of the prototype of the oil. Okay, that is how much? 3 into 10 to the power minus 2 twice. Then the oil is moving at the rate of, that is discharge, is equal to 3000 liter per second. 3000 liter per second. Okay. And tests were conducted on 15 centimeter diameter pipe. That means it is talking about model. Now the test is always done on model. So the diameter of the model, that is equal to 15 centimeter. So if you see, the prototype is having a diameter of 1.5 meter and model is having a diameter of 15 centimeter and is at the temperature of 20 degrees Celsius. Find the velocity and rate of flow in the model. So here we just find out the velocity in model and rate of flow, that is discharge. So this is for prototype and discharge is for model. We just have to find. Then viscosity is given, that is for the model. 20 years is 0.1 m is equal to 0.01 twice. Okay. So how to find this velocity and discharge? We just see that. So since it is a pipe flow, okay, so it is a pipe flow. So if you see a question in case of dimensional analysis, and that is about the pipe flow, you just use the Reynolds number or Reynolds model now. Use Reynolds number. Okay. So Reynolds number in you just see how to use that. Reynolds number in a model is equal to Reynolds number in prototype. So how to write Reynolds number? We just have seen this type of equation in a Reynolds model now. Okay. So if model and prototypes are given, so at that time we know the Reynolds number formula. That is that is equal to rho v d by mu. Okay. So again, in case of a prototype, we are writing the same formula rho v d divided by mu. So rho is for model. Okay, v is for again the model, and yes, this is p for prototype. On the right hand side, we just write p for the prototype. So again, we are just rearranging the terms, and so we just say we want in terms of velocity because we want to calculate velocity. So just take velocity terms on the left hand side, Vm divided by Vp. Okay, that is equal to rho m divided by rho p multiplied by mu m divided by mu p multiplied by dp divided by dl. Okay, density of model. How much is the density of just make one correction. This is model and this is prototype. Yes, now it is. So density of prototype is how much? That is equal. If you know the specific gravity is 0.9, so 0.9 multiplied by 1000. So you will get out that is 900 divided by density of model, that is 1000 because it's a water. Okay, multiplied by mu m, that is viscosity for the model. So 0.01 in terms of is okay, we just write it in a voice. So 1 into 10 to the power minus 2. 1 into same thing. If I write it in 0.01 or 1 into 10 to the power minus 2, one and the same. Okay, divided by 3 into 10 to the power minus 2. Okay, 3 into 10 to the power minus 2 multiplied by dp is what? The diameter of the pipe is, in case of a prototype, 1.5 divided by 15 centimeter converted into meter, so you will get 0.15. Okay, so if you do the calculation and find the answer, you will get approximately 3. So I just Vm for the model is equal to 3 Vp is for prototype. Okay, and the next thing is velocity of prototype. Okay, so but we got in terms of the ratios, that is Vm by Vp. Okay, that is equal to 3. So but we just want the constant value. So velocity of prototype, velocity of prototype is equal to, okay, so velocity we can also write in terms of discharge, that is equal to the rate of flow in prototype divided by area of prototype. Okay, that is equal to QP divided by AP. So QP is how much? That is discharge in a prototype is 3000 into 10 to the power minus 3 divided by area of the prototype, that is a 5 by 4 d square, means 1.5 meter square, that is equal to approximately, this is velocity for the prototype, that is equal to 1.698 meter per second. Okay, and if you put the value in the above equation, let's suppose we just say it as first equation. If you put this value in the first equation, you will get velocity in a model, velocity in model, okay, is equal to that is Vm is equal to 3 times Vp. So 3 times Vp, that is 3 into 1.698 is equal to 5091 meter per second. Okay, in the same way, you just find the rate of flow, that is discharge, rate of flow, okay, of model. So Qm is equal to Am multiplied by Vm, area into velocity. We know the formula. If you put all the values here, pi by 4 multiplied by area of a model means 0.15 centimeter square, that is meter square. We have converted into meter. Okay, multiplied by Vm, that is 50. Okay, 5 point. This is 5 point actually. 5.091. Okay, so approximately you will get the answer, that is 89.9 multiplied by 10 to the power minus 3 meter cube per second. So this is how you just have solved the problem for the distorted models by the Reynolds. Okay, so just wait for 10 to 15 minutes. I will again join here.